students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as semiconductors. Now, let's see what are the different types of semiconductors that we have, or let's see what are the different types of transistors that we have. Now, we had said that there are two different types of transistors. You have NPN transistors and PNP transistors. Let's see the symbols for them. For an NPN transistor, this is the base, this is the collector, and this is the emitter. So this is going to be my symbol for an NPN transistor. This is your symbol for NPN transistor, right? Now, similarly, you will have a symbol for PNP transistor, right? The symbol for PNP transistor, it is going to be the same thing except that the arrowhead will be inside. So your symbol for PNP transistors, the arrowhead is going to be inside. This is base, collector, emitter. This is PNP transistor. That's my symbol for PNP transistor. So you have two different types of transistors. You have NPN transistors and PNP transistors. Right? Now let us see how does a transistor actually work. Right? You have two PN junction diodes. How is it that the two PN junction diodes work together? Right? Let's see the action of transistors. Let's draw a transistor. Let's consider a PNP transistor. So you would have holes in the P region. You would have electrons in the N region, and again you would have holes in the P region. Right? Let's assume that this is my emitter, base, and collector. Now, we had said that the base emitter diode is forward bias. Now, if it is to be forward bias, that means I have to connect P-type, the positive terminal of the battery with a P-type semiconductor. This will make my base emitter diode forward bias. We also said that the base collector diode should be reverse bias. Reverse bias means the N-type semiconductor is going to be connected to the positive terminal of the battery. Right? Now, let's assume that IE is the current here. This is my emitter current. Right? Let's assume that IB is the base current here. And let's assume that IC is the collector current. Right? Now, the action for both types of transistors, whether it is PNP transistors or NPN transistors, is going to be same, except that there is going to be a difference between the majority and the minority carriers. Right? What we are going to do is we are going to study the action of a PNP transistor, where the emitter base junction is going to be forward biased with a potential of say VEE, and let us assume that the collector base junction is reverse biased with a potential of VCC. Okay. Now let's see the operation. The majority carriers in the emitter, that is holes, are going to be repelled by the positive terminal. Guys, the majority carriers in the P-type regions are going to be repelled by the positive terminal over here. Now, since the base emitter diode is forward biased, these majority carriers will easily pass into the base. Now, the base is extremely thin and is lightly doped, and hence it has extreme low density of electrons. Therefore, the holes that pass into the base, only few of them will recombine with the electrons. Most of them will drift across. Okay. only 2 to 5% will recombine with the free electrons in the n region and will be neutralized by the electrons in the n region. The remaining will enter the collector due to the potential that is applied between the base and the collector. Now these few holes that are going to be neutralized by the electrons in the base will constitute a small amount of base current. Fine, do we get this thing clear? Now the remaining holes which have drifted across the base enter into the collector and under the influence of the negative collector potential, the holes are going to be attracted towards the negative terminal, therefore they are going to move into the base. They are going to move into the collector and they will move out of the collector and that will constitute my collector current. Fine. I could use the Kirchhoff's law here where I could say that IE is equal to IB plus IC. The total emitter current entering the circuit should be equal to the total sum of the base and the collector current leaving the circuit. Fine, do we get this thing clear? So do we understand the action of a transistor? Let's see this. I can say that the majority carriers in the emitter are repelled by positive terminal of the battery VEE, right? Due to the forward bias of the emitter base diode, excuse me?
What does PE and CC?
That's just a naming given to it, right? Right. Due to the forward bias of the emitter base diode, these holes enter into the base. These holes enter the base, right? Now this constitutes the emitter current. This constitutes emitter current IE. That's how I'll get my emitter current. Now, the base is very thin and is lightly doped. Base is very thin and is lightly doped. Base is very thin and is lightly doped. Hence, it has low number density of electrons. It has low number density of electrons. When the holes enter into the base, only 2 to 5% of them recombine with the free electrons. Only 2 to 5% of them recombine with free electrons. Fine, do we get this in here? In the N region, the electrons in the base are neutralized by the holes, right? The electrons in the base are neutralized. The electrons in the base are neutralized by holes. So these electrons which are neutralized by the holes are replaced by some electrons which enter the base from the negative terminal of VEE. So electrons in the base which are neutralized Either holes are replaced by some electrons which enter the base from the negative terminal of VEE. Right? This motion of the electron forms the small base current. This motion of electron forms the small base current. That's how you're going to get base current, right? The remaining holes are able to drift across the base and enter into the collector region. The remaining holes are able to drift across the base. The remaining holes are able to drift across the base and enter into collector region and enter into collector region under the influence of negative collector voltage. Right? This constitutes collector current. This constitutes collector current. So that's how I'm going to get my collector current. Now, by Kirchhoff's law, I can say that the emitter current should be equal to the base current plus the collector current. IE should be equal to IB plus IC, right? Now that means I can say that the collector current is slightly less than the emitter current because some of the current is used as the base current. I can also say that collector current is a function of the emitter current. With increase and decrease in the emitter current, the collector current will also change. Fine, do we get this thing clear? Now, so do we understand the working of a transistor, how a transistor works? Now, when you have a transistor and it is put in a circuit, there are three different ways it can put in a circuit. I can put a transistor into the circuit in three different ways. Since it has three terminals, out of the three terminals, one terminal can be taken as common. So either I can have common base circuit, common collector circuit, or common emitter circuit. So there are three different types of circuit configurations under which a transistor can be put into the circuit. Fine, we get this thing clear? Next, types of circuit configuration. Types of circuit configurations. There are three different types of circuit configurations that you can have. One is common base. Second is common emitter. And third is common collector. So these are the three different types of configuration in which you can connect the transistor circuit. Because I want to forward bias one junction and reverse bias the other junction. There are two PN junctions. So one battery for each junction, and it's not that both the junctions are going to be connected in the same order. The emitter base junction has to be forward bias and the base collector junction has to be reverse bias. So that's the reason why I need two different power sources, right? So these are the different types of circuit configurations in which I can connect the transistor. Now the most common circuit configuration that is used is common emitter, right? So let us try to study the common emitter configuration. Let's see the circuit arrangement for a common emitter configuration. Let's take a PNP transistor. Right? Now, the base is going to be connected to a variable resistance. Which is then connected to a power source, PNP transistor, for forward bias. Right? Here you will have collector current and emitter current. This is my emitter, base, collector. And here again this is going to be connected to a variable power source through a variable resistance. The emitter is going to be common. The emitter is earth. Right? That's going to be my circuit configuration. I could have, this is going to be my emitter current IE, this is base current IB, and here you will have collector current IC. Right? That's how you would connect the given transistor in a circuit. So this is my circuit diagram for common emitter configuration. Fine, do we get this thing clear? Now, in the common emitters circuit diagram, or in the common emitter configuration, this is the most widely used configuration in which the emitter is earth, the base is used as the input terminal, and the collector is used as the output terminal. Here, emitter is earth, base is used as input terminal, and collector is used as output terminal. Fine, do we get this in here? So this is how you would connect the circuit diagram for a common emitter configuration, right? I can say that we'll call this battery as, say, VBB, and we'll call this battery as VCC. Okay, so I can say that the base emitter junction is made forward bias. Base emitter junction is made forward biased by battery VBB, and the base collector junction is made reverse bias while the base collector junction is made reverse biased by battery VCC. Fine, do we get this in here? Now, let us see the input characteristics for this, right? We know that the base emitter junction is going to be forward bias. So let us see how does the base emitter junction behave, right? Input characteristics. let's see the input characteristics. You would have, I'll just draw the graph and show it to you. This is my base emitter voltage in volts, and this is my base current in microamps. Right? You would have initially, as the base emitter voltage increases, there would be a very small increase in the current, and once it is forward biased, once the potential barrier is overcome, then it will behave like a conductor. So this is going to be my characteristics for this. Here, the collector emitter, the voltage between collector and emitter, you would get some voltage between collector and emitter. Fine, do we get this in here? So here, the graph shows, this is a graph between base emitter voltage and the base current for different values of collector emitter voltage. This is for collector emitter voltage 1. If I change the collector emitter voltage, then I can get a graph like this. This is VCE2. So for different values of collector emitter voltage, you would have different graphs, right? Now, for plotting the input characteristics, the voltage on the output side is kept constant. That means the collector emitter voltage is adjusted with the help of the potentiometer and is kept constant. Sorry. The base emitter voltage is varied with the help of the potential divider R1. We call this as R1 and we call this as R2. So I can vary the base emitter voltage with the help of the rheostat R1, right? And you would get a graph. Now every time the base emitter voltage would gradually increase from 0, the base current remains 0 so long as the base emitter voltage does not exceed the potential barrier. As soon as the base emitter voltage exceeds the potential barrier, the base current slowly increases and then turns into a large value. You can see that from the graph. Fine. So I can say that as the base emitter voltage slowly increases, the base current remains approximately 0 till the base emitter voltage overcomes the potential barrier till the base emitter voltage overcomes the potential barrier. As soon as the base emitter voltage becomes greater than the barrier, as soon as the base emitter voltage becomes greater than the potential barrier, right, the base current increases slowly, and then slowly, and then suddenly a large value, and then suddenly to a large value. Right, so that is going to be my input characteristic. Now let us try to find out the AC input resistance. I can say that the AC input resistance of the transistor in the common emitter configuration is defined as the ratio of the change in the base emitter voltage to the change in the base current. Now let us assume that delta VBE is the small change in the base voltage. Small change in base voltage. VBE. Okay, let's assume that delta IB is the small change in the base current, keeping the collector voltage constant. Small change in base current IB, keeping collector voltage constant, right? That is, I'm keeping VCE constant, right? Now in that case I can say that the input resistance, the AC input resistance RIN, is the AC input resistance. The AC input resistance is given by the formula delta VBE upon delta IB when VCE, when the collector emitter voltage is kept constant. Fine, do you get this thing clear? So this is going to be my AC resistance to the input signal that is sent in. Fine, do we get this thing clear? Now let us see the output characteristics. This is the input signal that you will see. Let's see the output characteristics. The output characteristics, let's draw the graph for output characteristics. Right, this is my collector emitter voltage. This is my collector current in milliamps. This is collector emitter voltage in volts, and this is for specific base current IB1, IB2, IB3. Right? So for different values of base current, you would have different characteristics. So here you have a graph of collector voltage with collector current for different fixed values of base current. Fine, do we get this in here? Now, if the base current is kept constant, if the base current is kept constant and then you plot a graph of collector voltage with collector current, then this is the graph that you will observe. Now, you can see that for fixed value of base voltage, the collector voltage is, if the collector voltage is increased, the collector current changes rapidly in the beginning and then it becomes constant and then it becomes almost independent of the collector emitter voltage, right? This constant value of collector current increases with the increase in the base voltage. So this is as good as your Zener diode in the avalanche, where the Zener diode in the avalanche is independent of the voltage, right? The current goes on increasing. Here the current remains constant and it is independent of the voltage again. Whatever is the change in the collector emitter voltage after a certain point of time, the current remains constant. Fine. So let's see this. I can say that for a fixed value of base current, as the collector emitter voltage is increased, as collector emitter voltage is increased, the collector current changes rapidly in the beginning, changes rapidly in the beginning. The collector current changes rapidly in the beginning, but soon it becomes almost constant. Soon it becomes almost constant. Soon it constant. Soon it becomes almost constant, and this constant value increases when the base current is increased. This constant value increases as base current is increased. Fine, do we get this thing clear? That means for a given value of collector emitter voltage, larger the base current, larger will be the collector current. For a given value of collector emitter voltage, larger the value of base current, larger is the value of collector current. Fine, do we get this thing clear? Now, what will be we found out the input resistance, let's find out the output resistance. Let's find out the AC output resistance of a common emitter configuration. Now, the AC output resistance of a common emitter configuration would be defined as the ratio of the change in the collector voltage to the change in the collector current, keeping the base current constant. So I can say that R out resistance is going to be the change in the collector voltage to the change in the collector current, keeping the base current constant. Fine, do we get this in clear? Now, let us try to find out. We found out the input characteristics, output characteristics. Let's find out the current transfer characteristics. Current transfer characteristics. Let's try to find out the current transfer characteristics. Let's see this, how the current is transferred. We are going to draw a graph of base current versus collector current. The base current is in microamps, whereas the collector current is in milliamps. What you see is that for a small change, you get a linear graph, keeping the collector emitter voltage constant. Keeping the collector emitter voltage constant, for a small change in the base current, there is a large change in the collector current, right? So the current transfer characteristics is a graph between the base current and the collector current for different values of collector voltage, right? Now, if collector emitter voltage is kept constant, if BCE is kept constant, then as IB varies, there is a change in IC. As the base current varies, there is going to be a change in the collector current also. So the graph between the base and the collector current is found to be a straight line. The graph between base and collector current is found to be a straight line. So this is going to be a straight line. Fine, do we get this in here? That means that the output current varies linearly with the input current, right? Now, if the output current varies linearly with the input current, in that case, what will be my AC current gain? Now, what is AC current gain? AC current gain is defined as the change in the output current to the change in the input current, keeping the collector voltage constant, right? The AC current gain is denoted by beta. AC current gain is denoted by beta. So I can say beta is the change in the collector current to the change in the base current, keeping the collector voltage constant. Fine, do we get this thing here? Now, so this was my current transfer characteristics. How do I use transistor as an amplifier? right? If there is going to be a current gain, that means a transistor can perform the function of amplification. Let's see how a transistor can be used as an amplifier. Transistor as an amplifier. Let us consider a PNP transistor. Right? The input signal is going to be given to the base emitter junction, where I'm using a common emitter configuration. So this is my input signal. This is the potential. This is my PNP transistor. So forward bias the junction. This is my potential to forward bias the base emitter junction. So this is going to be my base current IB, right? This is my input signal Vs. This is my constant potential VDD to keep, which is necessary to forward bias the base emitter junction, right? This is going to be my emitter current IE, right? You would measure the output across the load resistance. Now the output has to be reverse biased. So this is going to be my potential to reverse bias the output, right? This is my load resistance RL, across which the output is going to be measured. So the output is going to be measured across these 2 points. Fine. This is your collector base emitter. This is how you connect a transistor so that it can be used as an amplifier. Fine, do we get this thing here? You have 2 DC sources, one to forward bias the base emitter junction, the other to reverse bias the base collector junction. Fine. The AC input signal is given between the base and the emitter. Now we know that there is a linear current transfer characteristics. For a small change in base current, there is a large change in collector current. So depending upon the AC current gain factor, you would have amplified output. Fine, do we get this thing clear? So, do we understand how transistor can be used as an amplifier? Now let's try to find out the various equations of a transistor. Let's see what are the equations that are there in a transistor. First, I can say that the emitter current is nothing but the sum of the base and the collector current. IE is IB plus IC, right? Then I can say that the voltage across the collector emitter is going to be nothing but the voltage supplied VCC minus collector current into load resistance. That will be the voltage drop across the collector and the emitter. The voltage drop across the collector and the emitter is nothing but the voltage supplied minus the load resistance, the potential drop across the load resistance, right? Then I can say that the AC current gain, I already told you, is nothing but the change in the collector current to the change in the base current, keeping the collector voltage constant. Fine, do we get this thing here? Now, where the base current is in microamps and the collector current is in milliamps. Hence, I can say that the value of beta is much larger as compared to 1. Generally, the value of beta is between 30 to 900. So that is the minimum amplification that you can get is 30, and you could get an amplification of up to 900. I can also say that alpha AC is nothing but the change in the collector current to the change in the base current, right? Irrespective of the collector voltage, if you just measure the ratio of the collector current, sorry, not base, emitter. If you measure the sorry, if you measure the ratio of the collector current to the emitter current, then that is called as your current gain again, but here this is called as alpha AC, right? Now, voltage gain. How do I find out the voltage gain? Voltage gain is represented as AV, is nothing but voltage gain. That means it should be output voltage upon input voltage. Voltage by Ohm's law is current into resistance, so it should be output current into output resistance divided by input current into input resistance. So it will be nothing but delta IC upon R out divided by delta IB upon Rn. Fine, do we get this thing clear? Now, but we know that delta IC upon delta IB is nothing but the current gain. Therefore, I can say that voltage gain. Therefore, I can say that voltage gain is beta EC into R out upon Rn. Fine, do you get this thing here? Now, how do I find out power gain? I can say that the power gain is nothing but voltage into current, so it will be nothing but voltage gain into current gain, right? Voltage gain AV into current gain beta EC. So those are all the equations that are used in a transistor. Fine, do we get this thing here? Next, what do we understand by oscillators? Right? What do we understand by oscillator? Now, an oscillator is a device which generates alternating voltage. It may be defined as a circuit which generates alternating output signal which is required without requiring any externally applied input signal. Even though you don't give an input signal, it is capable of generating an AC output signal, right? So what is an oscillator? Definition. How do I define an oscillator? An oscillator is a device which generates alternating voltage. Which generates alternating voltage. It may also be defined as a circuit which generates AC output signal. It may also be defined as a circuit. It may also be defined as a circuit which generates an AC output signal, which generates an AC output signal without requiring any externally applied input signal. Without requiring any externally applied input signal. That is what is an oscillator. So in short, I can say an oscillator converts DC energy into AC energy at high frequency. So I can say that an oscillator is nothing but it is the exact opposite of a rectifier. What does a rectifier do? It converts AC to DC. What does an oscillator do? It converts DC to AC. Fine, do you get this thing here? So I can say an oscillator converts DC energy converts DC energy into AC energy at high frequency. Into AC energy at high frequency. Fine. So I can say that the function of the oscillator is exactly opposite that of a rectifier, right? Now, what's the difference between an amplifier and an oscillator, right? Let's try to find out the difference between amplifier and oscillator. Let's first see the block diagram for an amplifier. In an amplifier, suppose if this is my amplifier, there is going to be an input signal, there is going to be a DC source, and there is going to be an output signal. That's your basic diagram of an amplifier, right? So what is an amplifier? An amplifier takes energy from the DC source and converts an AC energy at the frequency of AC input signal. That is, the amplifier in an amplifier circuit, the frequency, waveform and the magnitude of AC power generated is controlled by the AC input signal. Right? Here you have a DC source which is converted into AC, but what will be the waveform, what will be the frequency, what will be the magnitude of the AC power that is generated is controlled by the input signal. So you can control this. Fine. Whereas in an oscillator, let's see the block diagram of an oscillator. Right? In an oscillator, you have just DC power input and you have an output signal. Right? So in an oscillator, the frequency, waveform and the magnitude of AC power generated is controlled by the circuit itself. In an amplifier, it is controlled by the input signal. In an oscillator, it is controlled by the circuit itself. That means there is no external voltage required, or there is no external controlling voltage that is there in this. Fine, do we get this thing here? So do you understand the difference between an oscillator and an amplifier? In an amplifier, it is the input signal that controls the output frequency, waveform and magnitude. In an oscillator, the output, waveform, magnitude and frequency is controlled by the circuit itself. Right? Now, what do you understand by feedback? What do you understand by feedback? And what are the different types of feedbacks? Now, the process of injecting a fraction of the output energy of some device back to the input is called as feedback. What is feedback? The process of injecting a fraction of the output, energy. The process of injecting a fraction of the output energy of some device back to its input is known as feedback. Right? Now, when we talk about feedbacks, there are two different types of feedback. I can have either a negative feedback or a positive feedback. Right? So there are two different types of feedbacks. First is a negative feedback. right? For example, let's consider that you have an amplifier, right, and you have a feedback network. The input signal is given to the amplifier, right? Now the input signal, this is my input signal V in, that is given to the amplifier. This is my input signal that is going to be given to the amplifier. Now the amplifier introduces a 180-degree phase shift. An amplifier will always introduce a 180-degree phase shift. It introduces a 180-degree phase shift, as a result of which my output from the amplifier is going to be 180-degree out of phase. This is going to be my V out, right? What we do is we take a part of this V out, give it to the phase, give it to the feedback network, right? Now since I want a negative feedback, in a negative feedback network, the negative feedback network introduces zero phase shift. And gives it back to the input. So you would have the feedback that would be given at the input would be 180-degree out of phase with the actual input, right? This is how your negative feedback network will work. Fine. So in a negative feedback, when the feedback energy is 180-degree out of phase with the input signal. So if the input signal and the feedback signal are 180-degree out of phase, then that is called as negative feedback. Fine, do we get this thing clear? Now, so that's my negative feedback network. Let's see a positive feedback network. Same thing you will have, first you will have an amplifier. Give it an input signal. This is the input signal that is given V in, right? The amplifier will the amplifier will introduce a 180-degree phase shift. Introduce a 180-degree phase shift, right? This is what the amplifier is going to do. Hence, my output is going to be 180-degree out of phase. This is going to be my V out. Give this output to a feedback network. Give this output to a feedback network. Such that you give it to a feedback network in such a way that the feedback network again introduces a 180-degree phase shift, right? The feedback network introduces a 180-degree phase shift, right? So in that case, my input signal that will go to the feedback network is going to be this way. The output signal from the feedback network is going to be this way. Hence, the feedback that will be given to the amplifier. So, this will be the feedback that will be given to the amplifier. This is how your circuit is going to work. Now, the phase difference between the feedback signal and the input signal is going to be 0. So, if the phase difference between the feedback signal and the input signal is 0, then that is called as positive feedback. Fine, do we get this thing clear? Okay, we'll stop this here for the day. Thank you very much.